is the chi-square test for homogeneity, and the second one is the chi-square test for independence. The difference of these two tests from the one that we saw last time, which is the goodness fit of test, is that the first one, the goodness fit of test, was only for one-way table. Like we can categorize we can summarize the data in one-way table. But these two types of tests, or chi-square tests, the data has to be summarized in a 2x2 or in a two-way table, which is something like this one. So on the column side, we have categories, and again here we have categories. So this is what we call a two-way frequency table. Therefore, both these, they are the use, or the data has to be a bivariate data, bivariate categorical data, which is summarized in a two-way frequency table. And this two-way frequency table, it has marginal totals. So these are the column total, and we call them marginal total. And again, we have the row marginal total, okay? And we have the grand total. This is what we call grand total, okay? So the grand total is sum of all the observations in sum of all the sets, basically. Or it's just sum of the row marginal totals, or it's sum of the column and marginal totals. So if you add this up, you get 300. If you add this up, you get 300. Or if you add all these individual cells, you get 300. So that's what we call the grand total. All right, so we use this information or this data to perform the chi-square tests. So the first one is the test for homogeneity. Okay. So in this case, we want to see if the distribution among the different populations or treatments is the same or not. So for example, let me change this font size because they are different. Select all of them. And let's keep it 16. Okay, and I still have some. Okay. All right. Okay, so the test of homogeneity, this one, this is basically comparing two or more different groups. If the proportion or if the categorical behavior among all those different populations is the same or not. It will be more clear when we see this using an example. And this type of test, or this kind of, in order to compare two or more populations or treatments, we use the chi-square test, which is exactly the same with what we saw last time. The formula is exactly the same. It doesn't change. And the idea, the concept is the same. The only difference is the purpose, okay? So for the first one, for the one that we saw last time, it was to compare P1, P2, and so on and so forth. If you have more than two groups, and if you wanted to see each proportion is the same with the hypothesized value or not, then we will use the goodness of fit, okay? But here we are checking the homogeneity among the groups. And you will see what I mean by this. Okay, for example, here we have Okay. Compare people who lived in a house or townhouse. This is one group. People who lived on the first or second floor, another group of an apartment building, and people who lived on the third or higher floor in an apartment building on the basis of heart attack survival rates. So, so for the heart attack victims, we are trying to see if it makes difference, whether you live in a house or townhouse, or living in a first or second floor or third or higher. Okay, does it make difference on the survival of the heart attack victims? And the data that we have, the count, we put it this way. So for example, from those who live in a house or a townhouse, in total we have this many, all these 5,531 individuals, they live in a house or townhouse, and they had a heart attack. Out of all this, 217 they survived, 5,000 they didn't. And apartment first or second floor, total we have 667 in our sample. Out of these, 35 survived, the remaining they didn't. And in a third or higher floor, we have 1,696, and 46 of them survived, and the remaining not. And the total the number of survivals is 298, and those who didn't make it, 7,596. And in total, this is the number of participants, or number of the sample size, or what we have in our sample. Okay, so notice that there were a total of this many victims, and out of this we have 298, and the proportion of total who survived is 0.03775. So to find the proportion of the total survival is this much, and those who didn't survive is this 7,596 divided by 7,894, or just 1 minus 0.03775, 1 minus this number. It will give you the ratio or the proportion of this number. Okay, this is the same with 7,596 over 7,894. If you divide this, you will get the same number. Okay, so in order to perform a chi-square test, whether it's goodness of fit or homogeneity or independence, we need to calculate or find the expected cell count. Okay, so for the goodness of fit, recall for the goodness of fit test, the expected, I will just use E to denote expected, is given by N times PI. Let me put I sub I here. So this is for the I's category. It is the same way, is equals to N times proportion, the hypothesized proportion of the I's category. So this is how we would calculate the expected count when we are working on this goodness of fit test. But here, for the test of homogeneity, the expected value or the expected count is given by this formula. Okay, so to find the expected value of this cell, there is a corresponding column total. This is the marginal column total. So we have a number here. Let me call this A. And then we have another total is here. Let me call it B. This is the row, this is the, here we have the row totals. This is the row total, and this is column total. Okay, column total. So the row total for this cell, because this cell is in, let's call it in cell 1, because we don't have another cell on top of it. So the row total of this one is A, and the column total is B. And then the grand total, let's call it C. Okay, this is the grand total. So the expected value, I will use E for this one. So E, let's call it E11, E cell column 1, row 1, column 1. Okay, this 1 means row 1, column 1. So the expected count for this cell is the column total, the row total, which is A, times the column total, which is B, divided by C. Okay, so this will give us the expected count of that cell. Now, when you go down the next cell, okay, the next cell to find this one. Now the column total doesn't change because all of them, they are in the same column. Okay, so this doesn't change, but the row total, because this now is in row 2, and if I call the row total for this one to be, let's say D, then E row 2, column 1, expected count of row 2, column 1 is D times B over C, and so on and so forth. And as we go this way, this direction, we change the column total. Just you take that column, the total of that column. So this is how we calculate the expected value. Okay, so for the example that we had earlier, the expected counts for the survival. So for this one, to calculate this, what we need to do is we multiply 298 times 5531 divided by the grand total, which is 7894. Okay, and when you divide, when you perform this, you get this number. Okay, and similarly for this one, to calculate this count, it's this times this divided by this one, and so on and so forth. For this one, you take this one, and this one. And for example, from the second column, to calculate this, the expected count for this cell is take this column total, row total, and then this column total divided by the grand total. The grand total doesn't change, but this one, always you take that total and this total. Okay, so here we have this table with the observed counts, and those in parentheses, they are the expected counts. Let me read this. Okay. Okay. So here, one thing that that we need to notice here is when you add this up, the expected, they have to add up to this number. Okay. Again, if you add this up, they have to add up to this number. And similarly this way, if you add this up, you get this number. So sometimes it could be off by some small number, and that is basically rounding error. So it's always good to be to use maybe 4 decimal places. At the end, you can round, it's okay. Here, for example, our textbook use 3 decimal places after the point. So for the last final answer, it's okay even if you use 2 decimal places. But when you do the calculation, for example, if you are using calculator, for example, let's say 2 divided by 5. Well, this is just 0.4, but let's, again, this is 3, okay. 3. Okay. So A divided by 3. This is 2.66, right? It goes like this one. So instead of writing 2.67, for example, in your calculator, if this is the final answer, then that's okay. You can write it this way. But if this is somewhere in the steps of calculating something else, then instead of putting 2.67 in your calculator, it's better to at least give more decimal place, at least 2 fourths. So this is more accurate than this one. Okay. Therefore, the rounding error for this one is smaller than the rounding error of this one. That's why that's how you could avoid these rounding errors. But yeah, sometimes you may see they may not add up to exactly this number. It could be off by a small number. But in general, the concept is that one. I mean, they should sum up to the row total or the column total. Okay, so now going to the chi-square test for homogeneity. The conditions, they are still the same with what we've seen last time. So the counts, they have to be greater than 5, all of them. We want all of them to be greater than 5. And of course, the samples, they have to be independent. They have to be selected independently. Or we need to have to believe, or we need to have a reason to believe that the samples is representative to the population. Okay. Once these conditions are satisfied, then the formula for the chi-square distribution is for the chi-square test is given by this. And if you notice, this is exactly the same with what we have seen last time. And that's what I was saying. The formula doesn't change. The formula is exactly the same. Okay. And this is how we calculate the expected count. Okay. And the degrees of freedom, this is one more thing that you need to remember. Degrees of freedom for, okay, let me put it here. Goodness of it. For this kind of test, degrees of freedom is just k minus 1, where k is the number of categories. If you have 5 categories, then it will be 5 minus 4, which is 5 minus 1, which is 4 degrees of freedom. But for this one, it is degrees of freedom is the number of columns, number of rows minus 1 times number of columns minus 1. Okay, so this is how we find the degrees of freedom for chi-square test of homogeneity. And then the hypothesis, we write it this way: the population or the treatments category proportions are the same for all of the populations or treatments. So we are saying the proportions are all the same. Okay, it's not like first proportion is this much, the second proportion is this much, or so on and so forth. We test whether the proportions are all the same or not. And the alternative hypothesis becomes the category proportions are not all the same for all of the populations. So going back to this example, what we mean by this is, for example, the survival rate, the survival proportion here. We are comparing the survival between these 3 groups, people who live in these 3 groups, if it is all the same or not. So basically, does it matter living here, here, or here? Does it make? This doesn't mean, like, let's say if the survival rate for this one is lower, it doesn't mean this has an effect. Okay, that's a different topic. That's a different thing. What we are seeing here, or what we are trying to know here, is if the survival rate here is the same across the different types of houses or the apartments, okay, or the floors. Okay. Now, going back to the example, that same example, we follow all the steps. So the hypothesis, we write it this way: proportions in each survival category are the same for all three groups. These are the three different houses or floors. And the method for this one is, of course, we are it's a hypothesis test problem, and we have three different populations. Okay, and the response is categorical, so we have to consider a chi-square test for homogeneity. Okay. Then we check the conditions, and the conditions, well, the samples were independently, they were representative samples, and the expected cell counts are all greater than 5. We've seen that. So, well, the chi-square test for homogeneity is appropriate, so we can perform this type of test because all the conditions are met. And then the calculation, well, we need to find the degrees of freedom, and the degrees of freedom is given by number of rows minus 1 times number of columns minus 1, and that's 2. 3 minus 1 is 2. 2 minus 1 is 1. So 2 times 1 is 2. So we have degrees of freedom equals 2. And the test statistic is given by this formula. And that's, you find the difference between the observed and the expected, square it, divide by the expected, and you do all this for all the cells. And the cells, by the cells, I mean this one. So what you do is you 17 minus 208.795 squared over 208.795 plus, this is for the first cell, and then you do this way. You could even go this way, it doesn't matter. Okay, then 5314 minus 5322.205 squared divided by 5322, and so on and so forth. So for each of them, how many summations you have for this one? 2, 3, 4, 5, 6. You don't need for the totals. Okay, it's only this one. So we do this, and then we find the chi-square, and the answer is 9.58. So we have the table in the book. You can access the book through WebAssign. So WebAssign, of course, you have access to the book. So you have the chi-square table in Appendix A, Table 5, or you can use technology as we did last time. And here we have the chi-square distribution. So we have degrees of freedom 2, and this is, I believe, 9.59. And here we have, you see, even the distribution, because the degrees of freedom is too small, the distribution doesn't look good. Okay, if you increase this one, it will get better. For example, 20, for example. See. All right, so this is the p-value, 0.00827. This is to be exact, but the table may not give you the exact value because you cannot find all the degrees of freedom in the table. Okay, but you can be systematic. Since 9.59 is between 9.21 and 10.59, both these numbers are in the table for degrees of freedom too. You can find both of them on the table. So since this number is between this one, the p-value of this one is between the p-value of these two. So what you could do is, instead of finding, if you cannot find this one in the table, you can find the p-value for this one and p-value for this one for the same degrees of freedom. And the p-value for this one is this guy, and the p-value for this one is this guy. Okay. Sorry, it has to be vice versa. P-value for this one. So this is for 10.59, This is 9.2. The p-value for this number is this, and the p-value is this one. And as you can see, we found the exact value using technology. And well, this is exactly between these two numbers. Okay. So what I am trying to say here is, even if you don't have the exact value, you can make decision just based on this one. Okay. Because what you need to decide, what you need in order to decide is just how small the p-value is. No one is going to ask you the exact value. Of course, when you do a research, people may want to see your p-value, of course, because instead of just telling them my p-value was too small, you have to show them that the p-value was actually small by writing the p-value. But as long as you write it this way, this is the same with mentioning it this way, writing it this way. So as long as you show the p-value is small, that's good enough. Okay. But when you use the technology, of course, the technology will give you the exact value. And well, if you have the exact value, you have to put that number. Well, now since the p-value is small, then of course H0 is rejected. So we would say there is a strong evidence that the proportions in the survival categories are not the same for the three groups compared. Okay. And it was kind of obvious. I mean, not obvious, but it was, you could suspect that one because the proportions were, the numbers were not close. As you can see here, the observed, here, for example, the difference between 35 and the expected, which is 25, are not, they are kind of far. Between 46 and 64 are kind of far, but we don't know how far, how significant this difference is. Okay. So, and the test, we found the test to be consistent with what we saw here. Okay, and the next one is the chi-square test for independence of two categorical variables. And this test, again, it's very similar in almost all things. Again, the only difference is the purpose of this test. So the purpose here is, instead of checking the homogeneity between, for example, the three different groups of apartments or floors, the survival groups, instead of checking or comparing the proportion for the three groups, here we check the independence between two categorical variables. Okay, if two categorical variables are dependent or independent, that's what we test here. Okay. And the assumptions or the conditions are all the same, and the formula the same. The how we calculate the expected value is again the same. Row marginal total times column marginal total. Degrees of freedom again the same. There is no difference. All are the same. The only difference here is how you write the hypothesis. So the null hypothesis becomes the two variables are independent versus the alternative hypothesis becomes the two variables are not independent. Okay. Or you can write there is an association between the two variables, and here you can write there is no association between two variables. So no association means independent. There is association means they are not independent. Okay. So that's the only difference. So otherwise we have to be careful whether it's a test for independence or a test for homogeneity, because they are very similar. And the way you put the table, it's very similar. It's a two-way frequency table. Now let's consider this example. Let's make this consistent. Okay, a researcher examined the relationship between a nurse's assessment of a patient's facial expression and the patient's self-reported level of pain. Okay, so when a patient comes to the clinic or hospital, the nurse will do they will do their own assessment just by the facial expression of the patient, and then the patient will report the level of pain. Now, will there be dependency between these two? Will there be association? Okay. And the way we put it, the table, it will be again a two-way frequency table. So here we have the self-report, no pain, pain. Okay. So this is the self-report, and the facial expression, no pain, pain. So from the self-report, we will expect this is the actual result, or the whether they had pain or not. They know it better than the nurses, because it's their own body. So in total, there were 20 of them who reported to have no pain, but out of these 20, 17 of them, they were correctly guessed by their nurses, and 3 of them, they were not. And those who reported to have pain, there were 69 of them, and 40 of them, they were correctly guessed, and 29 of them, oh no, 40 of them, they were not correct, because they said no pain here. Just by looking at the face, the nurses, they said they don't have pain, but they self-report, they said they had pain. But 29 of them, they were correctly categorized. So here the hypothesis becomes facial expression. This is one variable. Facial expression and self-reported pain, and this is the other one. And self-reported pain are independent, which means no association. And the alternative hypothesis, facial expression and self-reported, these are the two variables that we have, are not independent. Okay, so not independent means there is association. There is association. And well, the method is the same, and the degrees of freedom, 2 minus 1 times 2 minus 1, because number of rows, we have 2 rows, 1, 2, 2 columns, 1, 2. So 2 minus 1 is 1, 2 minus 1 is 1, so 1 times 1 is 1. Therefore, the degrees of freedom is just 1. And to check the conditions, the participants, they're thought to be representative of the population of nursing home patients with dementia. And the expected count, we have it here using the formula. We calculate all the expected count, and all of them, they are greater than 5. So both conditions are met. Therefore, here we have the table with observed and expected, observed, expected. Everything in parentheses is expected. And then the chi-square is 4.92. And again, we can use technology to find p-value. I have to change this one to 1. And this is 4.92. Well, here we have 0.0265. Yeah, approximately. Using the table, they found the p-value to be 0.025. And using technology, we found it to be 266, which are pretty close. And well, the decision will be the same. Therefore, because the p-value is less than alpha is this one, so even if you take this one, or whether you take this one or this one, it's still smaller than alpha, so we reject H0. And we would conclude, if you reject H0 was there is no association. There is no association, or they are independent. So we reject this one, which means there is association, or the two variables, facial expression and self-reported pain, are not independent. Okay, so here we can say there is convincing evidence of an association between a nurse's assessment of facial expression and self-reported pain. So this is all about chi-square test. So as a recap, the three different chi-square tests are the goodness of fit test, the chi-square test for homogeneity, and the chi-square test for independence. So three of them, they have similarities when you first see them or when you first learn them, but the purpose, that's the main difference among these three. Okay, the goodness of fit test is, it's one categorical, so that one is not a big problem to differentiate it from the rest, but these two, they are somehow confusing or tricky, so you have to work on that, and you have to understand the question, whether the question is about independence or about homogeneity. We have to understand that one. Okay. All right. So this is all for this lecture and for this semester, and I hope I know it wasn't the best semester that we would all dream about, but I hope we all get something out of it, and I hope the next semester will be better than this one. Okay.